Okay, here we are on my computer again, but I'm going to start a little differently than usual. Rather than working in MATLAB initially, I'm going to work in a program called MathCAD Prime. Now this is another number crunching program, and it's the easiest way I know of to beat numbers out of a computer. Now I know most of you are going to work in MATLAB, and we'll go to that here in a second, but I want to use it briefly to show how an integral transform would work. Now, one of the two most common integral transforms is the Fourier transform, and you can see it right here. The argument of the integral is a time domain function multiplied by e to the minus I omega t. And that e to the minus I omega t, that's the kernel function. And so what it does in practice is we use it to transform time domain to frequency domain. Now to show you how this works, I need a time domain function. So I've decided to use sine squared. And I'm going to do something very particular with it. Sine goes on in time forever and ever. It's perfectly localized in frequency and completely unlocalized in time. Now, I'm just going to look at what would happen if we had an impulse go into a system that was a sine squared function. So at time 0, the impulse started, and at time equals pi, the impulse ended, and at 0 everywhere else. So if you remember the expression for the integral transform, it goes from minus infinity to plus infinity. Well, in this case, no. From minus infinity to 0, the function is 0, and from pi to infinity, the function is 0. So the integral only has to go from 0 to pi now. Let's type that in here. I can just go up here to the math operator and just pull down this integral, and I want to go from 0 to pi. So I'm going to have sine of t squared. Now that's the function, time domain function. Now I need to multiply it by the kernel. Minus 1i is how you do this in MathCAD. Star t dt. Now the nice thing about MathCAD, it uses the same symbolic processor that MATLAB does. It's called MuPad, but it's a little more cleanly integrated into the software. MathCAD doesn't seem to much care whether you're working symbolically or numerically, and in MATLAB there's a pretty hard dividing line between those two. Now if I hit Control dot on here, that's a symbolic evaluation in MathCAD, and there it is. I'm going to put this down here. There we go. So there's what the Fourier transform of this sine squared impulse function. And if I want, I can now plot this. I'm going to go just grab a plot here. I'll clean this up here in a second. Just give me a second. Maybe. Okay, so I fit everything on the screen here. So I'm going to put omega there, f of omega. Now this isn't going to work, I don't think. Yeah, I didn't get anything. The reason is this expression is complex, and I don't know how to plot a complex function in just 2 dimensions here, unless I make it the absolute value, and now it should plot. Okay, there you go. Now, notice that that integral goes from minus infinity to plus infinity in time. The result goes from minus infinity to plus infinity in frequency. For our purposes here, I'm just going to use positive frequencies. I'm going to go from 0 to 50. There it is. Now, it's tempting to think there's nothing going on right here. You know, there's an initial lobe here, and there's a little bit of a bounce, and then nothing after that. Well, the reason you're seeing nothing after that is because I'm plotting it in linear amplitude. It's much more common to see things like this in log amplitude. So I'm going to go ahead and hit that. And if I want to 10 to the minus 20, that's kind of a little extreme. Let's go to minus maybe 8. There we go. Now, if there's a flaw with MathCAD Prime, it's that the plotting's a little rough. There's 2 different plotting functions, and they're incompatible with one another. They're different from one another. This one, this quick plot, will not allow me to label axes or put grids on it. If you happen to be in MathCAD and you want to do all that stuff, you have to go up here to Chart Component. But anyway, this is a pretty simple way to do the calculation and then to make a plot. And we can see that when you integrate in time with dt, the function comes out as a function only of frequency. The transform is a function of only frequency. And so this is how you look at frequency content of a signal. Okay, with that done, let's go back to MATLAB now and do some little more serious number crunching. Okay, now let's try that same calculation using the symbolic processor in MATLAB. First thing I'm going to have to do here is tell it what variables are going to be symbolic. So let's see, I'm going to give little f, capital F, omega, I'll just use a W for omega, and t. Okay, to keep things tidy here, I'm going to use lowercase f to include both the time domain function, sine squared of t, and the kernel function. So let me type that out here. Okay, there. That's the entire argument of the integral. And let's use capital F. We'll assign that the result of the integral to that. And remember, I'm doing this symbolically, so I'm going to get a symbolic expression. I'm going to integrate f with respect to what? I could be t or w, w standing here for omega. Well, I'm integrating with respect to t from 0 to pi. And there it is. Okay, let's plot this now and see what we get. So I'll say f plot f from 0 to 50. Now remember, we can't just do capital F. This is a complex number, so I need to plot the absolute value of that. And let's turn the grid on. There it is. Now there's one feature here that you might notice that appears here but did not appear on the MathCAD plot. I don't know if you can see that vertical dotted line right there. Okay, there's a numerical issue here. Let's go back and look at this expression. See the denominator right there? We have omega times the quantity omega minus 2 times the quantity omega plus 2. That denominator is singular at omega equal 2 and at omega equal minus 2. Now the entire expression is not. If I put omega equal 2 or omega minus 2 in for capital F, the entire expression does give you a finite value. And for reasons I guess I don't completely understand, MathCAD caught it and MATLAB didn't. So this is MATLAB talk for saying, I'm going to skip the undefined value there. Now, when we look at this, we have the same thing going on. This needs to be the vertical axis needs to be logarithmic. So let's just pull this up here. Let's go to Property Inspector. And if you go, I opened up, let's see, I had this open earlier. That was rulers. What it looks like when you first open up the Property Inspector is usually rulers is shrunk down like that, collapsed. So I open it up and let's see, let's go to y-axis scale, go from linear to log. And that looks better again. That's similar to what we had before. Let me make that a little heavier so you can see it. Again, opening Property Inspector, let's make it bright blue and let's make it heavier so you can see it. There. And if we want to, we can change the axes and everything, but you can see there's what this looks like in frequency domain. Now the horizontal axis here is frequency in radians per second. So that's an example of a transform. Now what would this look like in practice? Let me grab some examples here to show you. Go ahead and shrink this down here. Now, in another lifetime, before I was doing this, I was an automotive engineer in Detroit, and I was working in noise and vibration. So I did a lot of experimental work recording sounds and accelerations and things. And one of the things about engines is there's a pulse that goes through the engine every time the cylinder fires. Now, when the engine fires, or cylinder fires, a pulse goes through the engine, an acceleration basically, and that pulse is not sinusoidal, so it has several frequency components in it, and you can see those when you do run-up. Now, here's a picture of a calculation I did. There's a run-up on the left, and what we've got is time across the horizontal axis and frequency along the vertical axis. This is the result of another transform. It's not a frequency transform, it's a time frequency transform. So you can see not only what frequencies are present, but when they were present. And this fan pattern is very, very typical of linear run-ups on engines. And I can't remember if I synthesized this in MATLAB or actually measured this. I just don't remember. It's been too long ago. But you can see on the left is the time frequency distribution, and on the right is something called a power spectral density, and that's basically a frequency transform. So it's frequency on the vertical axis here and amplitude on the horizontal axis. So you can see those steps there represent the content of the three different orders you see on the left-hand side. And this is very typical of engine run-up data. You see this kind of thing all the time. Now, another recording I made, again a long time ago when I was still in Detroit, I recorded the sound radiated from an acoustic guitar, and I did it under very ideal conditions. The details aren't important here, but safe to say that I used a very, very high quality sound chamber and a lot of really expensive equipment, so it worked out really well. So let's go back to MATLAB here, and I'm going to clear this out. Whoops, clear it out. Yes, I did mean that. Clear the command window and see this. I'm going to pull this over so you can see it right there. That file right there, that wave file, that's the A string on the guitar. What I can do now is I've just right clicked and I'm going to say import data. Pull this down here and you can see the information about the data file, and it's asking if I want to import it. And so I've got, it'll call it data, and there's another variable called FS for sample frequency. So I'm going to go ahead and do that. Now you can see I've got, let's see, 882,000 points, and I've got 3 channels. I think they were all microphone channels, but let's just grab one of them. Let's say that X equals data, and I'm going to pick all the rows in one column. I definitely don't want to send that to the screen. All right, so you can see now that I've pulled out just that first column and assigned it to the variable X. Now this is discrete time domain data. This isn't a function. It exists only at discrete points in time, and you can see that the sample frequency is 44,100, which is the same sample rate that CDs use. And so that every 44,100th of a second, the data acquisition system grabbed a pressure really off the microphone and wrote that out in time. You know, can I plot that out? Sure. No, I'm just going to plot the vector out. I'm not going to make a time domain vector, although I could. Yeah, there's what time domain data looks like. I spent a large part of my life looking at stuff that looked just like that. And there's a story in there. What is it? I have no idea. I don't know what that is. Okay, it's not in a form that's very handy to me. So what happens if I transform that into frequency domain data? Let's see what happens there. Now remember, since this is discrete data, I can't use the Fourier transform integral. I'm using a discrete Fourier transform in MATLAB. Now, very seldom does anybody type in FFT in MATLAB. That's fast Fourier transform. That's the discrete transform operation in MATLAB. We almost always use something a little more refined than that. And I'm going to do something called a power spectral density. Suffice it to say that gives me about the same information, but in a much more readable form. Now, for reasons that make sense only to the folks at MATLAB, power spectral density is the command is not called PSD. It's actually identified by the algorithm. And the algorithm I'm going to use is called the Welch algorithm. Now I need to, there's a window length I have to specify here. So I'm going to make it 10,024 points. And I'm going to skip the details of what exactly I'm doing here unless you want a lesson in signal processing. But I've typed in enough information here to make a power spectral density and to do it in a way that makes it easy to look at. There's what it looks like. Let's just make this so you can fill the screen here. There we go. Now what's going on? You can see that there are frequency spikes here. And for a guitar, I would expect them to be a little more evenly distributed. I'm going to go ahead and make the window longer and see if I can identify some more of those peaks. Let's get rid of this. And let's multiply that by about 4 and see what happens. Yeah, there we go. That's way better. Now you can see all the notes from the string. Oops, there we go. I'm going to fill the window here. So you can see that there's a fundamental up here and then all the harmonics from that the string makes. Now what's going on up here? Why can't I hear anything above 10K? Well, probably the guitar's not making any noise above 10K, be my guess. Let's go ahead and zoom in here a little bit, see what we can find. There. So you can see those nice evenly spaced peaks. Those are the harmonics of the string. And you can see once in a while one of them's missing. Right there's one missing, is missing right there. One or two are missing right there. And the amplitude of the peaks are all different. Well, those amplitudes, those varying amplitudes as you go up in frequency, are what gives the guitar its distinctive tone, or they're part of it. That's how it shows up in frequency domain. So you can see here, we went from a time domain picture, which I couldn't make any sense out of, to a frequency domain picture that makes plenty of sense. I can tell all kinds of things from this. I can tell you whether it's in tune. I can give you a bit of an idea what the tone must be like, or just what components are in it. And in case you're wondering, no, I don't know how to look at this and tell you whether it sounds good or not. Knowing what frequency components are there is different than sound quality, so sorry about that. But the point is, we've gone from time domain to frequency domain, and that's that transform that makes integral transforms so useful and so important in engineering. So I hope this helps, and we'll talk to you next time.